Hello, everyone. We are Mr. McMahon's AVX group. We are developing an affordable solution for pollution monitoring with an aerial vehicle or a UAV. Uh, in our group is Jiang 12, Christian, Isaac, Komal, and then me, Rohan. So to begin with, our goal is to design a proof of concept and cost-effective pollution monitoring unmanned aerial vehicle.
So why are we choosing to use UAVs? In the past few years, there has been an overall trend of multiple industries transitioning from standard human-centered processes to UAV-centered processes, which can also be identified as drones in our case. The advantages of UAVs is that they're cost-effective and they have expanding sensing abilities, meaning they're able to cover larger distances of areas to measure.
UAVs present an opportunity for a more flexible and affordable solution for pollution monitoring. So UAVs attached with pollution monitoring devices can autonomously fly to diverse environments, rural or urban, high altitude or low altitude, while recording pollution data. Such UAVs can integrate machine learning algorithms and predict potential pollution sources and monitor pollution trends. There are already a handful of such pollution monitoring drones available on the market. Presented here are 3 such examples, and they range from around $6,000 to nearly $40,000. When the original drone's price tag is paired with repair and operational costs, the overall usage of a pollution monitoring UAV is extremely expensive and financially prohibitive for many people. Thus, our goal as a group was to design a UAV with the same capabilities as the more expensive drones, albeit with slightly lower quality, but at a much lower cost. So when designing our own pollution monitoring UAV drone, our primary focus was on reducing costs spent on the various hardware. The components displayed here are the hardware that we used for this project. Rather than purchasing a full kit, which are often very pricey because the sellers mark up their prices, we opted to buy individual components and assemble them ourselves. And while this approach did present significant challenges, which we will address later, it ultimately allowed us to create a functional UAV capable of stable flight using affordable off-the-shelf parts. This also made replacement costs very cheap as well. Over the course of our development, we had to replace 2 propellers, 1 flight controller, and 1 ESC, and all of those replacements total only costs an additional $100. So total on this project so far, we have only spent around $600, which is very cheap compared to the other drones. This was our roadmap for how we designed and built a drone. So first, we built a low-cost UAV that is both stable and powerful enough to carry additional sensors. Next, we developed a cost-effective pollution monitoring device based on Arduino-based sensors in parallel with the UAV. And we are now preparing to test this device by exposing it to precise concentrations of gases in controlled lab environments. And finally, we will integrate the pollution sensors with the original drone chassis and demonstrate our proof of concept by conducting a flight.
To measure these several gases, we decided to use an Arduino and 3 gas sensors. The gas sensors that we use can find nitrogen oxide, carbon monoxide, and also methane. Both nitrogen oxide and methane are both greenhouse gases that weaken the ozone layer in our atmosphere and causes harmful rays of sunlight to penetrate through the earth. Carbon monoxide is a colorless, odorless gas that can cause issues when inhaled, mainly health issues. And we decided to use an Arduino that will store the data gathered by the sensors and will create a graph based on the outputs from the sensors. In the future, we're going to try calibrating the sensors and test them in a controlled environment to see if they're accurate. We will probably test them around 20 degrees Celsius, where many of the sensors are most accurate, and we will see exactly what we need to change to the code, and also what we can change to the sensors to make sure that our results are the best that they can be. Finally, we will go on a predetermined path and test them in the real world to see if the readings are accurate or not, and if the code really works.
I wanted to touch a bit on the challenges during our development process. As the first ASDRP group to achieve a stable and balanced UAV flight, we faced numerous obstacles, even with tasks that we thought seemed really straightforward. So one significant challenge that appeared early during our development phases was hardware incompatibility. So as mentioned previously, to minimize costs, we opted not to purchase a full kit, but instead sourced individual components. But once we received these parts, we quickly discovered that many of them were incompatible. For instance, our propeller won't fit on the motor and the drone, and then the motor couldn't be mounted on a frame. And so in extreme cases, we had no choice but to buy new components that we double checked could be compatible, while in others, we had to spend additional time developing complex software protocols and designing 3D support structures to make the parts compatible. And our second challenge was tuning the drone. Unlike pre-tuned kits, our custom setup required us to start the tuning process from scratch, which involved weeks of trial and error. And those weeks of trial and error also resulted in numerous crashes of our drone, which caused lots of damage and required time-consuming repairs that delayed our development process and increased costs. Now I want to go over some of the limitations of our cheap design compared to the more expensive models. First, since we use cheap sensors, our data had very low accuracy. During testing, our GPS sensor, for example, showed around 5 meters of error, which was much larger than what we expected. The air quality sensors that Kristen was talking about also fluctuate in different temperatures and humidities, a problem that we are currently dealing with right now. We hope that by testing them under a controlled lab environment, we can increase their accuracy, but right now that is still something we are working on. Second, our flight time is much shorter compared to the other drones, so that limits the amount of data that our UAV can collect in one single flight. And third, our drone's radio is unable to transmit real-time sensor data, which limits the amount of real-time monitoring that we can perform. So here's a side-by-side comparison of our current pollution UAV, of current pollution UAVs on the market and our UAV. Current UAVs have very long flight times, they can collect very accurate data, and they have very reliable hardware at the cost of being not so cost efficient. On the other hand, our drone is is affordable, but it suffers from short flights, limited accuracy of data, and unreliable chassis. I wanted to end this presentation by touching on our group's future goals. In the near future, we hope to combine our drone with our pollution sensors, apply for a UAV license, and be able to perform several test flights with our completed system. And if we can successfully gather satisfactory pollution data, then our proof of concept drone is demonstrated. But if the drone is way too unreliable and it is not giving us a satisfactory performance, then our proof of concept will be invalidated. Thank you.